last time the main results and assumptions. So it's about type binding, and we had shown that for each k point belonging to the Bruyère zone, the type binding function binding functions that satisfy the Bloch theorem.
Sorry, are we recording?
Yes, I believe so, yes. Yes. So the type binding function constructed at a given k point from some specific atomic orbital, so that satisfies the Bloch theorem. And it's built from an atomic orbital so phi atomic for an atom mu, and of the type I, so 1s, 2s, and so on. So starting from this atomic orbital, we have seen that the corresponding type binding function at a given k point that satisfies the Bloch theorem has this form. C of kr is equal of 1 over square root of n, so n is the number of unit cells in the big piece of crystal one is considering with periodic boundary conditions for the wave function. One sums over the vector of the Bravais lattice, exponential ik times r times this atomic function mu for the atom mu and of the type r, and its center on the atom mu in the unit cell r. So we have seen that this is the form of the Bloch function constructed from a given atomic orbital. And we had written the wave function in the crystal psi or kr as a linear superposition of the type binding function for the lowest energy state in the atom. So we sum here over the atom, over the type of atomic orbital, and with some coefficient, and this is our type binding function of kr. So we had written the solution in the crystal for the electronic state in this way, on this basis, and in this we will take the lowest energy, so the lowest relevant atomic bond state. For instance, for a carbon atom, it would be the 1s, 2s, 2px, 2py, and 2pz atomic state. Okay, so this is what we had used as a basis for our Bloch function in the crystal, and then we are looking for the solution hc k is equal to epsilon k ck. So the solution for the crystal Hamiltonian for our electronic state in the crystal, and from there that we have derived a system of equations is what we saw last time. A system of equation that I had written last time. That was sum over the atom and the type of orbital of this matrix element between the type binding function mu prime I prime K R, the Hamiltonian, crystal Hamiltonian, and phi mu I of K R. So, and this matrix element time the coefficient, unknown coefficient, A mu I is equal to epsilon K, sum over mu I, and this overlap matrix element, mu prime I prime K R, phi mu I of K R, and the coefficient A mu I. Okay, this is what we had derived last time, and now we are starting from this point. And another thing that I told you is that in the tight binding approach, one writes the crystal Hamiltonian H as a sum, the kinetic part plus the sum of the atomic potential. So H bar square, gradient square over 2m plus sum over all the unit cell and all the atoms in each unit cell of the atomic potential mu centered on the atom mu in the unit cell R. Okay? So that's what we had last time. All right, and this is in the tight binding approach. Now we will make some further development of this. But as you can see in concerning this matrix element, in this and this, we will now work a little bit on this matrix element, knowing that these are the tight binding functions, and what we have to calculate in each of these cases is something of the type a tight binding function, mu prime I prime, so a given k point, and here we have a periodic operator. That is, if one translates everything by a lattice vector, a Bravais lattice vector, one doesn't change the Hamiltonian. The crystal potential is periodic, and the kinetic part also. So we have a periodic operator, an operator here that has the periodicity of the Bravais lattice. So O periodic. And we have the other tight binding function mu I K R. So in each of these cases, we have to evaluate something of that type. If it's the Hamiltonian, it's a periodic operator, and here it's just the identity, which is of course also periodic. So that's what we have to calculate in general, and this we can simplify this, knowing that the form of the tight binding function. So the tight binding function is 1 over square root of n. I wrote it before. And the sum over the Bravais lattice vector of this phase on the atomic function. So here I will use its explicit form. I get a 1 over n, sum over r prime, r, the Bravais lattice vectors, exponential minus I k r prime minus r. And then I have something of the type, a matrix element between the atomic wave function orbitals. So the atomic function on the atom mu prime of the type I prime, r minus d mu prime minus r prime. The periodic operator and the wave function phi mu I of r minus d mu minus r. Okay, so we have to evaluate this, but this metric element between this integration, because this operator is periodic, actually the whole the integral of what we have here, the complex conjugate of this, the periodic operator and this wave function, do not change when one translates by a Bravais lattice vector. So this integration here actually is the same as the integration of this wave function mu prime I prime centered on the atom mu prime in the unit cell R. So this is the same thing, the integration of the same wave function in the cell at the origin, d mu prime. The periodic operator times the atomic wave function centered on the atom mu in the cell r minus r prime. So okay, I need sorry. So this is the mu prime minus r plus r prime. Okay, so this is actually the same because this is a periodic operator, and one doesn't change this matrix element when one translates by a Bravais lattice vector. But I will just draw it maybe. What one has is a crystal, so I have my unit cells. And what I'm doing, so I have, let's say, in this cell, let's say I have my vector r prime here, and I have another vector that points to, let's say, this cell here. So this is the vector r. And I have an atom. Let's see, I'll take some color. So I have an atom, let's see, here in red, that would be the atom u prime. In this cell r prime, and then I have an atom in this cell r that is an atom mu, and I have some wave function centered on this atom and some wave function, atomic wave function, center on this atom, and I'm calculating the matrix element over a periodic operator that is invariant when I translate by any gravilattice vector. So basically, this integration that I'm doing, this function times this function over and times the periodic operator, is the same when if I integrate, I'm considering the origin here, and I consider the atom mu prime in the cell center at r equal to 0, and the atom mu in the cell r prime, sorry, r prime, r minus r prime, or r prime minus r. So this is the vector r minus r prime. So it's the same here if I integrate this wave function times this wave function in this cell here and here, using as origin I mean, when my origin is here, it's the same when if I translate and use as origin this, the wave functions on this atom, using this as the origin, and the function mu at the vector r minus r prime from the origin. I guess it's sort of obvious that the thing will depend only on r minus r prime. The product I will have will depend only on this. It's clear? Okay. So this integration will be exactly the same when if I translate everything by a vector r prime in this matrix element. Okay, so having simplified this, and now I can. All right, so this matrix element here, I mean, it's going to be equal. Okay. So I will have now, if I use the change of variable r second prime is equal to r minus r prime, I will have a sum over n, sum over the vector r, sum over the vector r second prime, exponential I k r second prime, and I will have this matrix element between my atomic function the periodic operator and the wave function ui at the position centered on the atom mu in the unit cell r second prime. Okay? Yeah? Sort of. Well, I mean, I guess you can just look at the metric element. You have something periodic here. If you change variable and use r minus r prime as r, small r prime, you just change variable. You don't have any change because of the invariance with translation of the periodic operator, and you just imagine you integrate over whole space. It's the same with periodic and boundary condition on the wave function when one integrates on a piece of crystal, and this matrix element, the integration is exactly the same as the translated integration here. So now that we get this, I took out the r, that is my integration or my sum here doesn't depend anymore on r at all, so I can simplify this and the n here, and I'm having just as a result for this tight binding matrix element the sum over r exponential I k r, and this matrix element with the wave function at the origin, the periodic operator, and the wave function in the cell r. That's the simplification. So with the tight binding wave function, one can simplify the double sum in just a simple single sum. Okay? All right, so that's the first simplification. Now, for the tight binding method, we will add some other simplification that comes from the form of the Hamiltonian. That is, we wrote the Hamiltonian using for the potential a sum of atomic potential, and we are going to use also. Okay, so now I want to further simplify my matrix element, and I'm looking explicitly at the matrix element with the Hamiltonian. So I want to further simplify this. And I'm going to use also the Hamiltonian, write it. So far I'm just using that. So I will have this for this matrix element, exponential IKR, phi atomic, mu prime I prime, R minus d mu prime, H phi mu I of R minus d mu minus R. Okay, so this is what I have to calculate. So far I only used this simplification. Now the Hamiltonian, I will write it in terms of sum of atomic potential, but I will sum and subtract the same thing in that. That is, okay, this is just the kinetic part of my Hamiltonian here. And I will just use the atomic potential for this atom centered on that atom, and I will add it and subtract it to the crystal Hamiltonian. So I will just rewrite my crystal Hamiltonian this way. And space. So this is my crystal potential, and I will subtract the same thing, the atomic mu prime of R minus d mu prime. So this is, well, okay, I just adding and subtracting the same thing. This, I'm doing this because I know that this is the atomic potential for this atom. Okay? So this part is just the atomic potential for the atom mu prime on the site at the position d mu. And the second part is just the crystal potential minus the potential on the atom we use as a reference that corresponds to this wave function. So this is called the crystal field, V prime of R. It is called the crystal field. And it is just, if you use as a reference this atom in the position d mu, it is just the potential created by all of the other atoms around this atom. So one removes the potential of the atom where this wave function sits, and one looks at the potential created by all of the other atoms. And this is called the crystal field. Okay, it's the field created by all the neighboring atoms. Right? So now the reason I separated this is that I know that this atomic wave function is eigenstate of this operator, it's the atomic operator. And then I will have matrix element involving this crystal field also. So I'm continuing. Can I erase this? Yes. This also. Okay, so this is what I'm using here. And I'm continuing, so this here. So now that I have split my Hamiltonian in these two parts, I will get, so I'm getting still this phase, and I'm getting as first part that is using this part that is the atomic potential. The operator is Hermitian, so I can put it on this side, and I'm getting just the eigenvalue here times this wave function, the atomic eigenvalue times this wave function. So I'm getting the atomic energy for the atom mu orbital I prime. The mu prime I prime r minus d mu prime the mu I r minus d mu minus capital R. Okay, and this is the first part. The second part is just the crystal field, and there I'm getting just only writing the same thing. So field mu prime I prime at this position d mu, the crystal field E prime of R, E mu I of R minus d mu minus capital R. Okay, so my matrix element, I already could use the information that is an eigenstate of the atomic Hamiltonian to simplify the first term, and the second term involves the matrix element of the atomic orbitals, with the operator, as operator the crystal field. Okay, all right. All right. So, but you can recognize here that if you now you have just a constant, so you can put the sum here, and this is nothing else than the matrix element between the tight binding functions. So now I can rewrite this as the atomic energy mu prime I prime, and I have my matrix element between the tight binding function mu prime I prime k r p of mu I k r. So I went back to the tight binding function, but now I have this energy in front. And the second part, I keep it as it is, so it is the sum of this phase and this matrix element which involves the crystal field. Right? No? Okay. Okay, so that is the result for the Hamiltonian. So in the end, from all this, we get for a system of equations from the beginning. This is a summary of what we got for the system of equations using all this. So what we got is this equation, system of equations. Where I'm writing the matrix element of the Hamiltonian between the tight binding function mu I and mu prime I prime and mu I. This is my coefficient mu I k for the block. For the crystal state is equal to epsilon k sum over the atoms and orbital type, an overlap matrix which I write A as A, mu I prime and mu I, and my coefficient a mu I of k, with this H, this matrix H, it has this matrix as matrix element mu prime I prime mu I, what we have found before, that is the atomic energy mu prime I prime and the overlap between the tight binding functions. So this is the Hamiltonian, the matrix element of the Hamiltonian. Okay, and I'm missing. The second part, mu prime I prime mu I. Okay. And this T are what we call the hopping terms. So these hopping here, mu prime mu I of k. We call them the hopping terms. And they are the sum over the Bravais lattice vectors exponential I k r times this hopping. The hopping comes from the fact that we evaluate between atomic orbital on different atoms the matrix element of the crystal potentials. So this is the atom mu prime orbital I prime. So it's the matrix element between this orbital on the atom mu prime. We have the crystal field here, and here it's the atomic orbital for the atom mu I. So sitting on the position dV at the position d mu in the cell R. So in this hopping term, we have a sum of this phase, which depends on the k vector and the Bravais lattice vector so we have the matrix element here between the atom centered in the cell at the origin at the position of the atom d mu prime, and on the other side here we have the wave function of the atom mu at the position d mu in the cell R. So we evaluate in these hopping terms the matrix element of the crystal potential over atomic function on different atomic sites. And finally, this A here is the overlap term. So this A matrix has the matrix element which are the overlap term between the tight binding function. All right. Okay, so that's what we get as a system of equation. We have this system of equation to get the energy, eigenenergy, and the coefficient of our crystal electronic state. The Hamiltonian involves atomic energy and overlap matrix element between the tight binding function. These hopping terms, which depend on k, and on the other side we have a matrix here, which is the overlap matrix between the tight binding functions. Okay. So this is in principle exact. We didn't make any approximation so far, except writing the crystal potential as a sum of atomic potentials. And we consider a finite number of bond states in our basis, which is also an approximation. But we can include as many atomic states as we want in this form. And now we are going to make further approximation in order to use also the fact that the tight binding functions are used in the case where these orbitals are localized, very localized, tightly bound to the atom. So the next step is to make some further approximation for this and for this, using the fact that the atomic states are very localized, the bond states are very localized. So, approximation. And here we are using the fact that what we use are very localized atomic orbitals. Okay. So, what we will use as approximation is that this matrix element, that is the overlap between atomic function sitting on different atomic sites, will be 0. So we will use this approximation that phi atomic for the atom mu prime with the atomic function here for the atom mu. So this we will write approximated as 0. When the vector here are non-zero, so when the atomic function are in different cells, we will say that this matrix element is 0. And when also the atoms are different, that is when mu is different from mu prime. So we will consider this non-zero only when we have the orbital on the same atom. Okay? So this is the approximation that corresponds to really orbitals that are very, very localized near the atomic site. And so we neglect the overlap when the atom corresponds to different atoms, when the wave function corresponds to different atomic sites. So in our system of equation, this will simplify very much what we had. Because we will have now for the overlap terms between the tight binding functions, so this A matrix, we will get, which was the sum exponential kr. So this is so the matrix this. Now with this approximation, we just include the R equal to 0, capital R equal to 0. This is just using this. So in different cells, the overlap for atoms in different cells, the overlap is 0. And now we also use that when mu prime is different from mu, this is 0. And when mu prime is equal to mu, it is non-zero only when one has the same I. That is, I prime is equal to I, because atomic orbitals on the same side are orthogonal. They are solution of the atomic Hamiltonian, and they are orthonormal, the atomic functions. So here we just get delta mu prime I prime mu I. So we just have the identity for the overlap matrix with this approximation. So this is for the overlap part, but also for the H part, that is the matrix element of the Hamiltonian, mu prime I prime mu I. This will simplify. We will have the atomic energy mu prime I prime, and also this delta mu prime I prime mu I plus the roping term. So the first part doesn't depend on K, only the roping term will depend on the K point. Okay? Alright, so that's our simplification for the type binding model. Now let's look at some example to see what kind of system of equation we have. We have seen that the system of equation that we had was in the form of matrix eigenvalue eigenvector problem. Now the overlap part on the side of the energy is the identity. So we have a rather simple system of equation that in the matrix vector form will be a matrix times a vector is equal to the eigenvalue times the vector. So if I consider, for instance, one atom per cell, and as atomic orbital, relevant atomic orbitals, the 1s, 2s, 2px, 2py, and 2pz orbitals, the problem that I will have to solve will be a matrix that will have as matrix element this. H will become the atomic orbital in the diagonal, the atomic energy in the diagonal. So for the 1s state, 2s state, and so on. It's going to be a 5 by 5 matrix with my 5 tight binding function from this 5 atomic orbital. So this is the energy here. Then I have this hopping term, T 1s of K. The same for the other diagonal term, so 2s of K. Off diagonal, I will have just the hopping terms. So I will have here T 1s 2s of K, and its complex conjugate here. And so on. So maybe I'll write the last one. I will have as last one here the 1s easy hopping term. And here the complex conjugate. So this is my H matrix. The vector are the vectors of the coefficients A, 1s, and so on up to A to B, Z. So these are the coefficients of the crystal state on the basis of, on the tight binding basis. Then I have the energy, epsilon k, and my vector of these coefficients, 1s to bz. So this is the system of equation I have to solve, or the matrix I will have to diagonalize to obtain the eigenvalue. So I have a 5 by 5 matrix to diagonalize to obtain the eigenenergies. And the eigenstates. Okay? So this is how what one has to solve in practice in the tight binding approximation. So like in the plane wave case, we are going back to this type of problems to solve a matrix eigenvalue eigenvector problem to solve. And with the overlap matrix going to 0, it is becoming much simpler. So this is going to give us the at a given k point the energies at each bend. We will have 5 solutions, 5 bends in this case, and we can get also the coefficient, the eigenvectors for the crystal states at this key point. So from this diagonalization, we will get the eigenenergy epsilon k, and we will have 5 solutions, 5 band energies, and we will get the corresponding crystal state, the Bloch state psi k j of R, which will just be given by 1 over the square root of n, the sum over the Rave lattice vectors, exponential kr, and the sum over the coefficient that we find from the diagonalization from the eigenstate. So the coefficient A Ji phi atomic of R minus capital R, in the case of 1 atom per cell. This is what one gets, and here the J, that is the eigenstate, go from 1 to 5. Okay? So this is these are the solutions in the tight binding model. Now I would like, and the solution are obviously linear combination of atomic orbital energy. Now, just want to make some remarks. When the lattice constant becomes very, very large in the limit where the atoms go, this means that the atomic sites will, the distance between atomic sites will become extremely large. So when in that limit, when the atoms are very far apart, that is when A goes to infinity or becomes huge. What one gets in the Hamiltonian is that the hopping term I prime I will go to 0 because this hopping term involves the matrix element of 2 atomic orbitals and the crystal field. So when the atomic orbitals are on different sides, this will go exponentially to 0 when A becomes very large, because the wave function decays exponentially from the place of the atomic site. And when one has the case where the wave function is the same, that is I prime is equal to I, because of the crystal potential that is on the atom sides only from the neighboring atoms, this also will go to 0, the matrix element, because the crystal potential will correspond to atoms that are at a huge distance. So also that matrix element, when I prime is equal to I, will go to 0. So all this hopping term go to 0 when A becomes, the lattice parameters becomes huge. And in this limit, what one obtains is just the diagonal part of the H matrix with as diagonal element just the atomic energy. So in that limit, one recovers the atomic energies. Epsilon E atomic, which makes sense. But what one can notice is that the wave function will be in a Bloch form. So the solution are Bloch functions. That is, the solution will be Ci of k r will be 1 over the square root of n sum over r exponential I k r, the atomic function Pi of r minus capital R. That is, the state will be a superposition of the same atomic state, but on different sides. I mean, this corresponds to Bloch states which have probability over the whole crystal. So the energy will be a flat band, and the crystal state will just be a linear combination of the atomic orbital, for instance the 1s, with this phase that is needed to have a Bloch state. Okay? So the energy are the atomic energy, and the wave function are these tight binding states. All right, so these were the two remarks. And now I would like to discuss some specific case. And the specific case which I will illustrate is the one of an isolated band in the tight binding model. So the case, special case that I will discuss now is that of isolated band. For instance, the 1s band of carbon in a crystal of carbon. This is a state that is well separated from the 2s and 2p state, and will give an isolated band in the sense that its energy will be very different from the energy of the higher states. There will be a gap, a large gap, between this band and the next bands. So in the case, for instance, of 1 atom per cell, one will have an isolated band that corresponds to its energy of this band being much smaller than the next one. So this would be for the 1s band in a carbon crystal, and in general one has an isolated band when its energy is very different from those above and those below. So epsilon minus 1 when one has this condition, one talks about isolated band, and in this case, if the matrix element of diagonal, that is the T open terms, TIG, are smaller than the difference between the energy of this band and those of the next one, or the one below if it's not a 1s band, then one can just use the diagonal part of the matrix to get the solutions. So here the approximation is the hopping term is much smaller than the typical energy difference between the band we consider and the neighboring bands. So if this is the case, we have seen that we can just use the diagonal part of the matrix, the diagonal element, and what we will get for isolated band epsilon I of k will be the atomic energy for that atomic state, and then in the sum I had over the lattice vector, the first element comes from the gravilattice vector r equal to 0, so this gives me this term, phi I r crystal field, phi I r, and the next terms are the sum over the other gravilattice vectors that are different from 0. So this hopping term phi I r phi prime phi I r minus capital R. Okay, so this is the diagonal element which corresponds to the solution when one has one is in the limit of an isolated band. So typically it's the case for the 1s bands in general. Now, when one looks at this, one sees that this term is nothing, it's just a shift, it doesn't depend on k. It's just an energy shift due to the crystal field. So the atomic energy will be just shifted due to the effect of the atomic potential of the neighboring atoms. And it's just the average value over this wave function of the crystal potential, crystal field. So this is just an energy shift due to crystal fields. Yes, you. So just a constant redshift. And the other element instead, it's a band dispersion. The other part will depend on K, so it will give a dispersion to the band. This part just gives a flat band, will just give a flat band. So this is what gives the dispersion, the band dispersion. And it is due to the interactions with the neighbors. K-band dispersion due to interaction. Okay? It's the matrix element that evolve with function atomic state on other sites than the reference site for that corresponds to this function, atomic function. So the dispersion of the bands measures the interaction with the neighboring atom. The larger the interaction with the neighboring atom, the larger the bandwidth. Okay? So in what will follow, we will make some further approximation. That is, in this sum, we will consider only the nearest neighbor. So in general, what we will do in the tight binding approximation is that we will consider only here the first nearest neighbor in this sum. So actually, not only for the isolated band, but in general, in the matrix, we will consider the Hoping term or the matrix element over the crystal field, only including interaction up to the first nearest neighbor. So for the overlap, we consider only what happens on the single site, that is, we neglect anything coming from the nearest neighbor, and for the crystal field, we include it just up to the first nearest neighbor in the interaction. So in what follows, so this is for the Hoping terms in the matrix in general. So the T mu prime I prime mu I in the sum over the lattice vector in the expression of this T, we will include, or we will neglect the interaction. We will include only up to first nearest neighbor, so we will neglect the interaction beyond that. So we will neglect the interaction beyond the first nearest neighbor. This corresponds to the approximation that we have very localized, well, approximation. We know that we have very localized atomic state. Okay, so this is what we will use as approximation for the hopping tubs. All right, so I have a little bit of time just to show you some examples, and I will consider the simplest case of 1s orbitals. So let's consider a simple possible case that is a 1D system, so a chain of atoms, and we consider just 1s orbital. So one has the case of an isolated band. And if it's the case of one S band, its energy is much smaller than that of the other atoms. All right, so in a chain of atoms, I will have my reference atom here, and I will have the nearest neighbor at the position A and minus A. So if I draw here the atomic functions, the phi, I will have that on the reference side. So this is my S function centered at the origin, and then I will have the wave function on the nearest neighbor. So phi S, let's see, at this position R1, which is A, and on the other side I will have the phi S at the position centered on the atom at the position minus A, and then just write this as R1 here is a minus. So this is the wave function. So on the left of my matrix element, I have this function, the complex conjugate that I'm integrating, times the function on the nearest neighbor, and the crystal field corresponding to this reference atom is the potential, that is the sum of the potential coming from the neighbors. So here I'm showing V prime of R. So V prime of R will be a potential that near this site will be of this type. I mean, it's going to be for sure attractive and, let's say, of this type coming from the first nearest neighbor. in particular. So the strongest potential will have this kind of behavior near this site and in the region where there is an overlap between the wave function of the nearest neighbor. So in this case, I will have the energy of my band epsilon s of k, which will be just kx in my one-dimensional system. So it will be the atomic energy. And then I will have the shift that I mentioned in the for the isolated band, and I'm writing it this way, minus delta V0, where this delta V0 is the absolute value of this matrix element, Vs of this wave function, the crystal field, which is here, times the wave function S. So it's the mean value of the crystal field. We know that the crystal field will be negative, so this matrix element is negative. I put the minus here and I'm taking the absolute value. So this is the energy shift. So the norm of this and the probability density of this times the potential, the crystal field integrated this. And then what comes from the nearest neighbor will be a constant for the first nearest neighbors, and it will be 2 times cos kx a. This comes from the sum over the 2 Rabi lattice vector R1 and minus R1, which will give me an exponential ikr, and I have here as matrix element T the Vs, the atomic wave function on my reference site, the crystal field, and the wave function on the neighboring site. So this matrix element will be negative also because I have the complex conjugate of this function times this function, and I'm integrating over a crystal field that is negative. So it will give me something negative. And of course, if I do it, this function times this function times this potential, and I integrate, I will get exactly the same thing if I take this function, and times this, and I integrate. So I will get the same value. I know that my matrix element in each case will be negative because the crystal field is negative here. So I put a minus, and I'm getting this. The cos comes from the two-phase exponential I kx a plus exponential minus kx a, which comes from these two R vector corresponding to the nearest neighbor. Okay, so this is what one gets for the S function in the one-dimensional case. So one just has a cosine as band distortion. So if I draw it, my energy as a function of k in the Bruyère zone, so from pi over a, between pi over a and minus pi over a. Here I would have the atomic energy of my S state. Then I have this shift, will shift my average energy down by the quantity delta V0. And then I have a minus cosine, so I will have something that goes like this, around this average value, and the width of my band here will be 4 times t, because cosine goes from -1 to +1, so I will have a bandwidth here which will be 4 t. So this is the result for the 1s band in 1 dimension. I will just do the case 2-dimensional for the S state, because then I would like you as a homework to do a 3-dimensional case for the S bands. So just in the 2-dimensional case, if one considers similarly an S band or S orbital, if I consider the square lattice, that is, I have my reference site and I have my neighbors on the square lattice like this, X, Y. So I have the reference site with my S orbital here, and I have the first nearest neighbor that will be at R1 here, minus R1 here, and R2 here, and minus R2 here, and each of them has an S orbital on its atomic site. So in this case, what I'm getting for the diagonal element that corresponds to this S band will be an energy epsilon S of K, which will be the atomic energy of the S band plus the metric element PS on the reference site, the crystal field, and the same function. So this is just the shift, which I call delta V0. It's the same argument. The potential that comes from the neighboring side will be negative near this orbital, so I expect a negative value for my matrix element, minus. So this is just the shift, and then we have the 4 nearest neighbors, so we will have exponential ikxa for this site with the wave function phi s of R crystal field and function at the site R1. So this is the first contribution that comes from the wave function on this atom with the crystal field. Then I have the contribution coming from the other neighbor on the other side. So I'm getting exponential minus kxa, the phi s of R v tilde v prime of phi s of R plus R1 this time. So it's from this time, this site, and then I have the contribution of this atomic state and this atomic state. So I will have exponential I k y phi s of R v prime R S of R minus R2 plus the last neighbor that is giving me this phase exponential minus I k y a and this matrix element. Alright, so these are all the contributions that I will include when I go up to first nearest neighbor in the type binding approximation. Now, all of these matrix elements are the same in the square lattice because I'm integrating this wave function times this wave function and my crystal field that has the symmetry of the square lattice that is invariant under any kind of rotation of 90 degrees or reflections. So if I calculate this matrix element, this function times the crystal potential and I integrate, I will get exactly the same thing if I take this function and the crystal potential, because there is a reflection symmetry. I have exactly the same potential on each by reflection. It's invariant under reflection, and the matrix element I will get will be exactly the same for these two atoms, and they will be also the same for these atoms. If I integrate this times the crystal field, it's the same thing whenever I integrate this and the crystal field, because I have this 90-degree rotation for the crystal potential. And all the wave functions are also the same here, 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 and here. So all of these matrix elements here are the same. So this is the same, and this is the same, and this and this one is the same, and this one. Okay, so in the end, what I'm getting is just epsilon s minus delta v0 minus 2t. I will call all of these t. Well, actually, I know it's also negative because my crystal field is going to be negative in the region where we integrate the wave function. So all my matrix elements will be negative. So what I'm obtaining is minus 2t cos kxa plus cos kya. So the cos ky comes from these two exponential, and the cos kx comes from these two exponential. So this is what one gets for the square lattice for the S orbit. Okay? So also cosines. Dispersion that again measure the band is also going to measure the interaction with these neighbor atoms. Okay, so I will stop here. You will see the case of 2p state next time. Any question?